In previous video, we look at how can we use Excel to get our regression equation and how should we interpret a partial coefficient. And in this video, we will look at how can we find our coefficient determination from Excel and where should we find SST, SSR, and SE from the Excel output. So, as we learned in the simple linear regression model, and we know SST equal to SSR plus SSE. So this equation is also held in our multiple regression model. The SST, the total sum of the square error, equal to the sum of square error expanded by the regression model plus the sum square error. So the calculation for SST, SSR, and SSE doesn't change. So yi, the observation minus mean of y powered by 2, and sum all of them together, you will have SST. And the estimated of y hat minus the mean of y powered by 2, and sum all of them together, you will get SSR. And the observation minus the estimated of y, the y observation powered by 2, and sum all of them together, you will get SSE. Now what we will do is we will recognize where can we find SSR, SSE, SST. Actually, we will find from the old place. Do you remember in the simple linear regression model in the last week class I mentioned the regression output have three parts: regression statistics, ANOVA table, and the regression equation. And in order to find SSE, SSR, SST, you just need to look at ANOVA table. So the column label is SS, stands for sum square error. So the sum square error explained by the regression is 143. So that is our SSR. And the SSE is sum square residual, that's 56.95. And if you add SSR plus SSE, you will get 200. So this is SST. So we know if we want to calculate the coefficient determination, and we will use SSR divided by the SST, and we will get our R square. So after you do the calculation, and you will use 143 divided by 200, and you should get 0.7165. So now let's go back to look at our original Excel output. Do you find the R square here, 0.7164, is exactly what we got here, 0.7165. So instead of doing the calculation for coefficient determination, our Excel will tell us where is coefficient of determination in our first part of the output, regression statistic. So the R square here is our coefficient of determination. So in order to interpret this value, you should try to remember what I said before. First, convert it to percentage. So that is 71.65. So that means 71.65% of variation in the new coming customer is explained by our regression model. So obviously, the model has a very good goodness of fit because this percentage is over 50%. So our model did a good job than the mean of our y variable. So the next statistic we'll look at is adjusted multiple coefficient of determination. Before we learn the multiple coefficient of determination, but this one is adjusted. So what will be used to adjust our coefficient of determination? So let's look at the background. So adding the independent variables, even ones that are not statistically significant, cause the prediction error to become smaller, thus reducing the sum of square due to error. So the SSE will decrease because we add more independent variables. Because SSR equal to SST minus SSE, when SSE becomes smaller, so SSE becomes smaller and SST doesn't change, so which means the SSR will become larger, so which are causing the R square to increase. So if R square increase, and we will know the model have the better goodness of fit. Unfortunately, this increase is caused by increasing more independent variable. So this will give people the wrong idea that is if you want to have the good model, you need to increase the number of the x variable. However, if you increase the number of x variable, you will cause a complication of the research. So that is not the statistician looking for. So what they will do is the statistician create a new statistic to measure the goodness of fit of the model called adjusted multiple coefficient of determination. So that statistic will compensate for the number of the independent variable in the model, which means if you add the number of the variable will become like a penalty on the value of your R square. The more, in the other word, if you are increasing the number of independent variable, you may not have an increasing adjusted multiple coefficient of determination. So this statistics is more popular used than the coefficient of determination itself. So let's look at how should we calculate the adjusted multiple coefficient of determination. So what people usually do is first calculate the coefficient determination and use 1 minus the coefficient of determination times n minus 1. So we know that n minus 1 actually is the observation minus 1, and the denominator is n minus p minus 1. That is a degree freedom of our SSR. So by plugging the value, we got 0.6031. So this is our adjusted multiple coefficient of determination. So before we got about 70, the original coefficient of determination is 71.65%. However, we can find that the adjusted multiple coefficient is relatively smaller. It's 60.31%. The reason it's smaller because the whole statistic is penalized by the number of the independent variable. So now I want to let you know, instead of to do the calculation to find the adjusted coefficient determination, you also can find it from our Excel output. Again, look at the regression statistic. And the adjusted R square is below our R square. So that is our adjusted R square. Instead of doing the calculation, you can directly find the statistics from the Excel output. So in our next video, we'll look at how should we test the significance of our regression model.